Hello everyone, welcome to this online course on material science. This is lecture 20 in the module 1 on magnetism. And if you recall, in the last 3 lectures, I believe, I have introduced 3 different types of angular momentum of an electron, right? And they were L, which is the orbital angular momentum operator of an electron. Then the second one was the spin angular momentum of an electron, and then the last one that I have talked about was the total angular momentum, right? Momentum, and all these angular momentums are for one electron. Now the question is that usually what we measure in response to some magnetic field in a material is the magnetic moment, right? You remember. And the magnetic moment was a vector in classical electrodynamics. But in quantum mechanics, since magnetic moment is a measurable quantity, right? The second postulate says that any measurable quantity should be or can be represented by an operator, right? In that sense, the measurable quantity, which is the magnetic moment of an electron, should be an operator. So I'm just putting a hat to indicate that that's vector operator. And this magnetic moment will be due to one of these or all of these angular momentums, right? The question is, how do we relate the measurable magnetic moment of an electron with L, S, or J, right? So that's our goal in this lecture. So the first thing to note is that the magnetic moment, right? So mu is a general notation for the magnetic moment. And the subscript L is denoting here that this is a magnetic moment due to orbital angular momentum, right? Orbital angular momentum. So how do we relate the orbital angular momentum with this mu L, right? So the magnetic moment due to orbital angular momentum, which is an operator, is related with the angular momentum of orbital angular momentum of an electron by this relation. So we have some factor here, which is the charge of the electron, which is minus C, times some factor GL subscript L, and then twice the mass of the electron, right? Here we know all of this quantity, and the new one is that the GL. So this GL is known as the G factor of an electron, right, for its orbital angular momentum, right? That's what GL is. It's a number momentum. And for our purpose, this GL is 1. So you remember that GL should be 1. But now I want to manipulate this expression to bring it in standard form, where I can say that, you see, I can introduce a factor of h bar in this problem, and then so I'm just writing in such a way that this h bar appears, because this is, if you recall in our previous lecture, is the Bohr magneton of an electron, right? And we also have some factor of GL here. And that's why angular momentum due to the orbital, or sorry, the magnetic moment due to the orbital angular momentum is denoted by GL times the Bohr magneton, right, which is mu b, and then we have factor of 1 by h bar times the orbital angular momentum, right? That's how we denote the relation between the mu L and the L, right? Similarly, the question we can ask is that what is mu s, right? So that's also a vector. This is nothing but the magnetic moment of an electron, but now due to its spin orbital, which is the subscript s, right, is spin angular momentum. And the relation is that mu s, which is the magnetic moment operator due to spin, is related with the spin operator as vector hat, which is the vector operator. By this relation, again, the charge of the electron times some g factor, but now it's for the spin, divided by twice the mass of the electron, right? Similarly, in this relation, we can introduce a factor of h bar to, sorry, there should not be any minus sign. So E times h bar divided by the twice m and 1 by h bar, a spin operator, right? So from this you can see, and that's your Bohr magneton of a single electron. So the magnetic moment due to spin angular momentum is related by Gs mu b divided by the h bar times the spin operator, right? So that's the moment due to spin. So the question is now, what should be the total magnetic moment, right? Because you see the electron has orbital angular momentum and a spin angular momentum. So the total moment should be adding up these two components, right? So we are adding the orbital angular momentum operator with the spin magnetic moment. So this was the magnetic moment due to the orbital angular momentum, and this is magnetic moment due to the spin angular momentum, right? And if you replace these two quantities, right, this one and this one, in the place of mu L and mu S, you can see this quantity can be written as mu b by h, and then we have GL times the the orbital angular momentum operator times GS times the spin angular momentum operator, right? And these two values, like GL and GS, is known, right? And let me give it to you. So as I have mentioned before, GL is 1 and the G factor for the spin angular momentum is 2 for the electron, right? We will use these two values in this expression. Then you can see the magnetic moment, the total magnetic moment mu is mu b by h, and here I have L plus twice the spin operator, right? So everything in this bracket is our operator. Now you remember, right, that this quantity can be written in this form, right? Because we are just expanding the 2s, and then we have outside we have the mu b by h, right? The factor multiplying this number. So what is L plus S? In the previous class, you know this, that's the total angular momentum, right? So mu b by h j plus S. So that's the total angular momentum operator. Let me put the hats just for consistency. So that's we have a hat here also. So the total magnetic moment of an electron is equal to minus Bohr magneton by the h bar, and then we have total angular momentum times or plus added with the spin angular momentum. That's an important relation. So one thing to remember is that whenever we are writing this magnetic moment expression, let's say this one, you can see this magnetic moments is g times some factor mu b by h times the corresponding angular momentum, right? When there is L, we have L here. If you look at the same, the spin, the magnetic moment due to electronic spin is minus g of factor of the spin, which is gs, times some factor which is known mu b by h times the spin operator, right? And here we have also the same relation. Now the question is, can we write something similar for the total magnetic moment? Because here you see we are adding j plus s, right? But can we write the total, the question is that can we write the total magnetic moment of an electron in terms of some g factor times mu bh, and we know this is a total magnetic moment, so it should be related with the total angular momentum of the electron, right? The question is, can we write the total magnetic moment in terms of this total angular momentum of the electron? And this is a known factor, and the question is, what is this g? So my plan in the next lecture is to show you, usually this g is known as the Landé g factor, right? So how many g factors we have seen in this lecture? One is the g factor for the orbital angular momentum gl, which is 1. One is g factor due to the spin angular momentum, which has a value of 2. And here I am introducing another g factor without any subscript, or in some textbook you will see this is also written as gj. So it's as though it's a g factor, but for the total angular momentum of the electron. Now the question is, our plan is to write the moment in this form, and now we have to find out what is the value of this Landé g factor in terms of a known quantity, and I will explain how do we find the expression for this Landé g factor. The reason why we need this Landé g factor, because we are going to understand the quantum mechanical framework for the paramagnetic ion, right, or paramagnetic atom. So in that case, we will need this total angular moment and the magnetic moment operator, where the Landé g factor will be an important quantity in the expression, right? That's why we need it. So for this lecture, that's about it, and thanks for listening.